from Genique. So this is the next question. It's a very conceptual question, and by using this question we will solve 2 to 3 questions based on this, and it is a perfect application of this question is the perfect application of the Gauss law. Okay, so read that question. Calculate the electric field intensity. Calculate the electric field or electric field intensity at electric field intensity E. Electric field E at R by 2 and 2R. At R by 2 and 2R distance due to the charged sphere of radius R, okay, with volume charge density rho v. We have to find, there is a volume charge. There is a sphere consisting of a volume charge rho v. There is a sphere is there of radius R, okay. There is a sphere. There is a sphere of radius R. So observe this. There is a sphere like this of radius is what? Let us suppose this is the center of radius R. How much? Capital R. It is the capital R. Okay. It is a sphere. So it is consisting of full of what? It is consisting full of charged particles, because it is a having a volume charge density of rho v. Okay, so it is having the volume charge density of rho v. The figure is not given. Okay, so it is having a volume charge density rho v. Okay, now what we have to find? Due to this, it is a charged sphere. It is a charged sphere. It is having volume charge density rho v. Now we have to find the electric field intensity at R by 2 and 2R. Due to this, it is a charged sphere. Okay, it is a charged sphere. Now observe this. So we have to calculate electric field intensity. R by 2 means mid distance of this, and at 2R means outside this. We have to find the electric field intensity due to this, inside and outside this. So how can we find this type of, how can you find how to approach this kind of questions? So Gauss law only. Okay, so we know how to use Gauss law for finding the electric field intensity. Okay, for finding the electric field intensity from the Gauss law, what we have to find? Where we have to find the electric field intensity, where we have to find the electric field intensity, choose that point. You consider, you construct or you consider one closed sphere. That closed sphere is called as the Gaussian surface. You have to consider the Gaussian surface. Okay, you have to consider the Gaussian surface consisting of the radius at which you have to find the electric field intensity or electric flux density. Understand? So where you have to find? You have to find inside. R by 2 means inside and outside. R by 2 means at mid distance. Okay, I will give a generalized formula. Okay, for this, after that we will put R by 2 and 2R. So that means, so not only, see, now I will calculate the electric field intensity not only at R by 2. Okay, so we will derive some generalized formula, and that generalized formula is applicable for all the problems which are having the questions which is inside the, where we have to calculate the electric field intensity inside the sphere. Okay, so now let us suppose you consider you have to find the inside, right? First of all, I am considering the inside. Now somewhere I am considering this one Gaussian surface. I am constructing one Gaussian surface. This is the blue pen representing one Gaussian surface. Okay, it is at a distance of what? It is having a radius small r. It is having a radius small r. Okay, to apply the Gauss law, What is the Gauss law is saying? The Gauss law is saying that is what? Closed integral d dot ds is equals to q. The charge enclosed, okay? Charge enclosed in the volume or q. Charge inside. Okay? D dot ds is equals to q, closed integral. You know from this, because it is uniformly charged rho v, here the d is same everywhere. This is from the center, the d is same everywhere. So you can write this d outside, right? So d into integral ds is equals to q enclosed, charge enclosed. So from this, what is this integral ds? Integral ds is the surface area of this considered sphere. Okay, where I am calculating? I am calculating inside this. First of all, what is this? It is inside the sphere. Inside the sphere where r less than capital R, you consider this is the first case. Okay, inside the sphere I am calculating the r less than r. So that means what? It is the Gaussian surface I consider where I have to calculate the electric field intensity. Okay, so on this Gaussian surface the strength is same everywhere, so that's why I am writing this d outside. Understand? So now I have to find this closed surface. What is the closed surface I have considered? I have considered this closed surface only. Okay, what type of closed surface it is? It is a spherical surface. So I can write d into, what is the integral ds is s. Integral ds is s means what? It is s means what? 4 pi r square. It is the surface area of the sphere. It is the surface area of this sphere, 4 pi r square, inside sphere. Okay, it is equals to, what is the charge enclosed within this volume? I have to write charge enclosed in this Gaussian surface. What is the charge enclosed in this Gaussian surface? We know rho v. Okay, we know rho v. Okay, rho v means volume charge density. To find the charge, what I have to do? I have to multiply this volume charge density with the volume of this sphere only. So what is the charge enclosed within the Gaussian surface? The charge density within the Gaussian surface into the volume of this Gaussian surface. So what is the volume of this Gaussian surface? 4 by 3 pi r cube. Okay, the volume of the sphere. Which sphere? This sphere, inside sphere. Okay, so from this 4 pi will get cancelled, r square is also cancelled. Here d, here you will get rho v into rho v r divided by 3. So this is the electric flux density at inside this is what? R less than capital R. This is the generalized formula and it is very important relation. So from this, what is the electric field intensity? The electric field intensity is equals to rho v into R divided by 3 epsilon. Right? These two are very important relations. These two are very important relations. Okay? This is inside. Understand? This is very important relation. Now, observe this. So, what we have to find? You have to find the electric field intensity at R by 2. So, this is for what? R. This is for R less than R. These two. Okay. So, to find the electric field intensity at R by 2, what you will get? The electric field intensity at R by 2, what happens? R by 2 is equals to, put R equals to R by 2. So at a distance of where? You have to find at R equals to R by 2. Okay, suppose this is the R by 2 here. Okay, let us suppose. So you have to consider this as the Gaussian surface at R by 2. Okay, so if you put R equals to R by 2, you will get the electric field intensity at R by 2. Let us suppose this is R. let us suppose this is r by 2. Okay, this is r by 2 radius. At r by 2 radius, but r by 2 is also inside. So I can apply this formula at a distance of, this is not small r now. Okay, so I can apply this formula because it is where this formula is applicable up to where? This formula is applicable up to, from where to where? This formula is applicable from here to here, up to here. This formula is applicable wherever you want to find. You can replace this r by the given r, but it is inside, right? You can also represent, you can write the, in place of r, you can write r by 2. So that means rho v into r by 2 divided by 3 epsilon. This will be rho v r divided by 6 epsilon. So this is the electric field intensity inside. Understand? Now what we have to find? The next one is what? You have to find the electric field intensity outside. So if you want to find the electric field intensity outside, so you have to consider one more Gaussian surface outside, right? I have to find the electric field intensity outside. Let us suppose at some distance r, I have to find the electric field intensity outside this sphere. Okay, so this is the one more Gaussian surface. It is one more Gaussian surface. It is having a radius some r. I am also representing this one as a. This problem is completed. Next, coming to the next problem. Okay, so this is what? R. Okay, I am calculating the electric field intensity or electric flux density outside the sphere, the given sphere. The red circle represents the red sphere represents the what? The sphere given. Okay, now apply the Gauss law for this. Suppose if you apply the Gauss law, how can we apply the Gauss law? The closed integral, what is the Gauss law? Gauss law is saying that closed integral. Now the second part is what? Outside the sphere. Outside the sphere, r greater than capital R. This r is greater than the actual radius. The actual radius is what? Capital R. Understand? Of the sphere. Now apply the Gauss law. What is the Gauss law is saying? What Gauss law is saying? Closed surface integral d dot ds is equals to charge enclosed or q enclosed in the volume. Okay, so now, so you know, because of this sphere, because the point where we have to find the electric field intensity or electric flux density, this point is on the sphere, the electric field intensity is constant because these all points are equidistant from the center of the sphere. Okay, so now I can write d into integral d dot ds, integral ds is equals to charge enclosed. So d into what is this? I have to consider this Gaussian surface, right? Now this is the Gaussian surface. This one is the Gaussian surface. Gaussian surface is nothing but it is the closed surface on which we have to calculate the electric field intensity or electric flux density. Now what I am finding? The net flux leaving this closed surface. What is the net flux leaving this closed surface? To find this, I have to consider the d on this closed surface. So because this d is constant, I am writing this outside. Understand? I am writing this outside, and next what I have to do? I have to find the surface area of this Gaussian surface. What is the surface area of this Gaussian surface? It is 4 pi r square. Now this is the r now. Understand? This is r. This is r. Okay. Now this will be equals to charge enclosed in the volume. What is the charge enclosed within the Gaussian sphere? Within the Gaussian surface? This is the Gaussian surface. What is the actual charge is enclosed? Only this amount of charge is present within the Gaussian surface. This is very important. So within this Gaussian surface, this blue line, so this is the actual, this red pen is the actual Gaussian surface. This red pen is the actual sphere of volume. Only this sphere is consisting the charge. This sphere is containing the charge. So that's why, what is the charge included in this total sphere? What is the charge included in the total sphere? The charge included in this the total sphere is what? Rho v into, but q is not given, right? How can we find q? The total charge within this means, see, this white is nothing but what? It is outside, right? There is no charge here. Only this amount of portion is having the charge. So that's why the q enclosed is equals to, the charge enclosed is equals to rho v into the volume of this sphere containing the charge. Okay, rho v into 4/3 pi r cube. What is this pi r cube? Pi r cube means what? This is capital R cube. Why? Because only I have to consider this surface only, because only the sphere is containing the surface. Of sphere is of how much radius? Capital R. So if you are writing the small r means it's gone. It's gone. Okay. So where you have to write the small r and capital R is important. Okay. So now this 4 pi is gets cancelled. So from this d can be written as what? Rho v r cube divided by 3r square d. So 4 pi will get cancelled, dr square, it is 3r square, it is rho v r cube divided by 3r square. So this is d. Now what about E? E is equals to, this is one important relation. Now E is equals to rho v r cube divided by 3 epsilon r square. Okay, 3 epsilon r square. Okay, how the electric field is directed? The electric field is directed radially outward. Okay, we concentrated only on the magnitude here. The electric field is directed radially outward. So this is the thing you should observe. Okay, this is very good conceptual question. Okay, one should understand what is, so for the better application, if you know the exact application of the Gauss law, you should solve this. Okay, you should understand this type of questions. So this is rho v r cube divided by 3 epsilon r square. So now what you have to find now? So this is for what? This is for r greater than capital R. This is outside the sphere. This is r greater than capital R outside the sphere. Now what we have to find? Suppose if you put E, suppose if you want to find electric field intensity at E at 2R. So what is the question? Next question. It is, we have to find the electric field intensity at 2R, right? Wherever there is a small r, you have to put 2R. Okay. I have to calculate the electric field intensity 2R. Let us suppose R is equals to 2R. Okay. So I have to write, because this R is constant, capital R is constant. Okay. So here rho v r cube divided by 3 epsilon, what is this r square? 2r whole square. So this will be rho v r square means here it will be here it will be r divided by, it is 12 epsilon only. So this is E at 2R. So this is the answer. Rho v r divided by 12 epsilon. Okay. So for the given question, the answer is completed, and these star mark relations are very important. Okay. So now observe one thing. So from these two we can write one relation. Okay, we can write a graph. So what is the graph is saying? That is what the graph is saying, that observe this. Due to the electric field, okay, observe this. The electric field intensity with respect to the radius, okay, and the distance within the closed sphere, and this figure is only for this question only. This figure is only for this question only. Okay, so now observe this. Observe this. So come to this. See, I am drawing the electric field intensity versus radius graph. Okay, so wherever, see, observe this, I am going from 0 to outside of this R. Okay, let us suppose at some place at R. So observe this, you observe this question. See, the electric field intensity within the radius, what happens? Means when the electric field intensity up to R less than R means, up to R means what happens? It is a rho v, 3 epsilon is a constant. This is entire thing is a constant. But electric field is varying with respect to R. It is linear variation because this entire portion is what? Constant. So that means E proportional to R. So that means in this what? E is proportional to R. E is proportional to R means what? This will go like this, linearly varying. Up to where? Up to the radius. So how it is varying? From here to here, from here to here, what's happening? The electric field will be, as distance increases, the electric field also increasing. Okay? Now, as after R, what's happening? After R, this is the main. After R means what? After capital R greater than R. You have to consider this expression. So in this expression, what is this? This is the constant and this is also constant. Capital R is constant because it is a constant sphere. Already the radius is given. This is also constant and this is also constant. This entire portion is constant, but it is what? 1 divided by R square. 1 divided by R square represents a non-linear variation, decay. Okay, as R increases, what's happening? R increases, the electric field will be decreasing. So this is the thing, you have to identify this. Okay, so at R equals to R, what's happening? At R is equals to R, if you put R equals to capital R, what's happening? If you put R equals to capital R, what it will be? Rho v into R divided by 3 epsilon. If R equals to capital R, what happens? Rho v R cube divided by 3 epsilon capital R square. Rho v R. So these two will become same. Now at R equals to R, what is the value? The value will be E is equals to what? The E will be is equals to what? Rho v into capital R divided by 3 epsilon. Okay, both the values are having this. So this is the thing, and this is very important, this graph. So up to the radius it is increasing, and after this it is decreasing, electric field intensity. This question is very important. Okay.